Assalamu alaikum. Let's now discuss the other applications of this equal area criteria. In this case, we'll see the concept of critical clearing angle and critical clearing time. Let us say we have a system, synchronous generator, which is connected to an infinite bus through a transformer and a transmission line, and we assume that a fault is occurred in between the line, which results zero electrical power that is sent to the infinite bus when this three-phase fault occurs at this point. Now, let us say our system is operating at point delta naught with mechanical power Pm and electrical power, let us say it is Pe naught, and the system is stable. Now if three-phase fault occurs at this point, which results that Pe is equal to 0, there is no electrical power that is flowing from this side to this side. So when three-phase fault occurs, electrical power reduces to 0. You can see there will be no electrical power. Electrical power would have been this, since it's it results in a three-phase fault. Electrical power will be 0. We can see electrical power follows this. So the accelerating power will be simply equal to Pm, because P is equal to 0. Accelerating power will be equal to Pm. So the accelerating area will be the area between Pm and P is equal to 0, that is this line. Let us say we are clearing the fault at delta 1 and we are restoring the power. We are restoring the power. When we restore the power, again this Pe now will be this curve, P delta curve. This will be the Pe. Since we are clearing the fault at this point at delta 1, that's what I have shown, a fault clearing angle at delta 1. Now the electrical power has restored to Pe, that is this Pe. Now there is the decelerating, suddenly decelerating power has appeared. It will result in deceleration, as we have discussed earlier. So the deceleration takes place from this point to this point, so that the different things happen which I have told you. Now the system will be stable this when this area comes out to be, this area A2 will come out to be this area A1, and that happens to be at this point delta 2. From now onwards, the first case which we have discussed in the last lecture was the increase in the mechanical power. From now onwards, we will keep the mechanical power same, which will be the actual case, and there will be the change in electrical power. Electrical power will change, mechanical power will remain the constant. Like here, electrical power reduces to 0, and then suddenly it changes to other value, or we can say it restores to the original value, which results in deceleration. When it reduces to 0, it results in acceleration, and when it reappears, it results in deceleration. So this is the during fault P is equal to 0, P is greater than 0, it results in acceleration and then deceleration. This happens. But if we here we have cleared the fault at delta 1. Let us say we not clear at delta 1, we'll clear at this point. You can see this area has to increase now from this point to this point, so that this area A2 will be equal to this area A1. Now we will discuss the limiting condition. That is, this concept of critical clearing angle and the critical clearing time is the same thing. But here we are discussing the critical clearing angle. That means the angle at which we clear the fault before it goes to the unstable, before it loses its synchronous. That is, let us say that angle is this. When this area, accelerating area, it covers, and it has some decelerating area which is just equal to this accelerating area. So we can say, we can calculate in this case delta CR. So using the equal area criteria, A1 is equal to A2. That means the area under this delta naught to delta CR, PM d delta should be equal to integral of this, that is PE minus PM from delta CR to delta max. It should be equal, this should be equal. Now PM, when we integrate it, since PM is constant, this will remain to delta, that is delta CR minus delta naught, and integral of P max sine of delta minus PM delta delta. So this is P max cos of delta CR minus cos of delta max. Because this will be equal to delta max, this delta max will of course be equal to pi minus delta naught minus Pm delta max minus delta CR. This delta max is equal to pi minus delta naught. I have shown you in the previous lectures also. Now taking Pm to the left hand side, this Pm will come to this side. This Pm delta Cr minus delta naught plus this delta max, that is equal to pi minus delta naught minus delta Cr. The delta Cr and delta Cr will cancel out, is equal to P max cos of delta Cr minus cos of pi minus delta naught. The cos of pi minus delta naught will be equal to plus cos of delta naught. So this will be like this. This will be equal to pi minus 2 delta naught. So Pm divided by P max minus cos of delta naught taken to this side divided by then cos of inverse. So delta Cr will be equal to cos of inverse Pm by P max pi minus 2i delta naught minus cos of. You can see it from here. This critical clearing angle, it depends upon this uh, disturbance is in this case Pm. You can see the disturbance is Pm because here electrical power reduced to 0, and here it also depends upon the delta naught, that is the initial operating condition, which we have already discussed theoretically. Usually, but the power system engineer is interested in critical clearing time rather than the critical clearing angle, because when we set the different relays, in relays we don't set the critical clearing angle, we set the critical clearing time. So we need to find out the critical clearing time. During the fault, P is equal to 0, swing equation will become h by pi f del square delta by del t square is equal to Pm, of course, in per unit. Del square delta by del t square is equal to pi f by h Pm. Integrating with respect to P, we get delta by del t, which is equal to pi f Pm by h into t plus omega naught. So it will be equal to pi f by h Pmt with respect to rotating field. Then this will be equal to 0. So delta, then again integrating, delta will be equal to pi f h Pm, that is t square by 2 plus delta naught. So this is, now t will be equal to twice h delta minus delta naught pi fm whole square root. At delta is equal to delta Cr, T is equal to TCr. So we can get the TCr value like this. So the system will be stable if circuit breaker clears the fault before TCr or delta Cr. So circuit breaker had to clear the fault before this. If it does not do this, this delta Cr will, if it, let us say, clears at this point, so this area will become more, and it does not have area which is decelerating area which is equal to this area. So in that case, it will lose the synchronism. So we have the value of the TCR. Here it usually we calculate it from the swing equation, this TCR, and critical clearing time is always calculated from the swing equation. But here it was easy because for the case which we have discussed, P is equal to 0. This P is equal to 0 makes this equation very simple and linear equation. When P is not equal to 0, we know that P is itself non-linear. It makes the equation non-linear also. One more thing, lower the value of delta naught, higher will be the value of TCR. You can see it from here. So TCR will have the higher value. We can say higher will have. Therefore, higher will be the chances for the system to regain stability. So here also we can use the discussion that we have already concluded, that is delta naught. This transient stability also depends upon this delta naught. Now the next case is sudden loss of one of the parallel lines. You need to be very careful about this. Please try to be very attentive. These are two circuit breakers. Sudden loss of line, it can be any reason. For the time being, instantaneous. We can say this is the sudden loss of instantaneously. We lost one of the parallel lines. So this is the equivalent circuit of this system before the occurrence of the fault. So let us say in this case x equivalent is equal to x d dash plus the parallel combination of x1 and x2, that is x1 parallel x2. Similarly, then P will be equal to EV by x equivalent sine of delta. So usually when power transfer happens between the two voltages, so power transfer will be equal to the maximum power transfer will be the summation multiplication of the voltage divided by the total impedance seen by the two voltages. So that is why I have written over x equivalent here. So this will be EV divided by XD dash plus X1 parallel X2. Immediately after switching up the line 2, the equivalent circuit will be like this. Now X equivalent will be equal to XD dash plus X1. So PE2 will be equal to EV by X equivalent 2 sine of delta, that is EV divided by XD dash plus X1. So here X equivalent 1 will be less than X equivalent 1 is this, will be less than X equivalent 2, because this parallel combination will be definitely less than this. So EV divided by X equivalent 1 will be greater than EV divided by X equivalent 2. We can say P max 1 it will be greater than P max 2. So when we draw PE1, that is P max 1 sine of delta, and PE2, that is P max 2 sine of delta. So it will be like this. This is P max 1 sine of delta. This is P max 2 sine of delta. Only difference will be the peak of them. P max 2 will be less than P max 1. Now it is operating at point A at angle of delta naught before the loss of line. When loss of line occurs, this PE1 changes, the electrical power changes from PE1 to PE2. Now here it suddenly changed from PE1 to PE2. Here there is some, when this happens, you can see that some accelerating area or accelerating power is available at the rotor and it will accelerate. And same will happen from this to this, because now the electrical power available and electrical power delta curve will be this, not this one. But the transient, it will change from initial operating point to this, and then it swings forward and backward at this point, as we have discussed earlier. But definitely there is a good amount of area available that we have assumed the system will be stable in this case. You can see it here. So it swings forward from point B, C, let us say this is D, then D, C, and A. And in this case, since the system is stable, this uh, area will be equal to this area. And for the limiting case, you can see that this delta 2, because the curve will be now this, when let us say it is more less, you can say lesser than this value, limiting case, this area will be equal to this whole area. In that case, this delta max will be equal to pi minus this delta 2, that is delta CR, critical clearing and limiting case. This delta CR will be pi minus delta max. Delta max will be this, or delta max will be equal to pi minus delta 2, and this delta 2 will be equal to sine inverse of PM divided by P max 2. We can calculate it also, because at this point PM will be equal to P max 2 sine of delta 2. From this point you can calculate the delta 2 and then delta max. Now the next case, sudden short circuit on parallel lines. We have to see what will happen to the system, how the system behaves when some short circuit occurs on the parallel lines. Let us say first case, when the short circuit occurs at this point, which is very close to the circuit breaker, and this circuit breaker is close to this bus. That means whole line will be towards this line. When this happens, it is as good as the fault occurs at this bus. It is as good as, because from here to here it remains the short circuit, or can they at the same potential. But from here to here is the transmission line. This is the transmission line. The equivalent circuit for this system is like this. We don't have a fault at this point. We can say that a fault, this is the second case, when the fault occurs away from the line. Because here the case 1, short circuit on one end of the line. That means at this point, when one end, since these two are connected in parallel, it means whether the fault is at this point, 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 it is one and the same thing, because they are at the same potential. So the equivalent circuit will be like this, and the fault can be shown like this. Let us first calculate the electrical power before the fault occurs. That's the normal operating system. Pre-fault, that is before the occurrence of fault, the power angle equation is given by, that is PE1 will be equal to v xd dash plus x1 plus x1 parallel x2 sine of delta. That is the earlier which we have discussed. So p max 1 is equal to sine delta, that is p max 1 is equal to ev uh, xd dash plus x1 parallel x2. When the three-phase fault occurs at point A, let us say this point A, no power will be supplied to this infinite bus. When no power is supplied to infinite bus, this will be equal to 0. Pe2 will be equal to 0. Since I have told you these are all the situation where we assume Pm is constant, and we will see what will happen when electrical power changes differently. Now the circuit breaker of the line 2 will operate and the line 2 will be open, that is this, and fault is cleared. Definitely when the fault is at this point, which we have assumed, and this circuit breaker will open the line. Now the electrical power will be restored through line 1. There will be some power which is supplied to this infinite bus through this line 1. Power angle equation is given by, suppose post fault power angle equation is Pe3 is equal to EV xd dash plus x1 sine of delta, which is equal to P max 3 sine of delta, which is equal to, where P max 3 is equal to EV xd dash plus x1. The only difference from the earlier case, from this case to that case, is that we are assuming this is opened simultaneously. There is no interval between the opening of this line and the initial operating condition. But here we have assumed that fault is occurred and the power that is supplied to the infinite bus will be 0 in between the restoring of the opening of the line. Now plotting PE1, PE2 and PE3 on the same graph, we get this is PE1, because PE1 you will have less xd dash plus x1 x1 parallel x2, that will be less than the. This is PE3. In a real case we have assumed this to be PE2, this will be similar, and PE3 will be nothing but this curve, that is x-axis or delta axis in this case, which is on a delta axis Pe is equal to 0. Pe2 will be equal to 0. And let us assume we are clearing the fault at delta C, because delta C in earlier case sometimes we can see it at delta 2 and Pm has increased to some Pm1 or Pm2, but here we are definitely naming this delta C as clearing angle. Now this is the accelerating area. Now at this point fault has cleared and PE has restored to PE3, because now you can see it from here. PE3 will be there because line 1 has been opened. So PE3 will be restored, PE will be restored to PE3. Some power is supplied through line 1. Now the electrical power will follow this curve. So for a stable system, this will follow this curve and area 1 will be equal to area 2 for this case. In general case, when we have some area available, this area available apart from this A2. For this case, this area 2 will be equal to area 1 and the system will be stable. Similarly, this is the limiting case, this one, when this delta C, that is the cleared angle, is equal to delta CR, that is the limiting angle, at which this area A2 is just equal to this area A1, and this is actually used to find out this delta CR. Here this delta P max will be equal to pi minus delta 1, because it is, this point is very important and we have to see it when this point is always with respect to the available electrical power curve and the mechanical power, because this point can be this point can be this, here are two, this point can be this also, because we have one electrical curve like this, because since now the electrical power which is now restored is only this, that means this will be the delta max. So delta max will be now equal to this, delta naught will be equal to sine inverse Pm by Pmin. So delta naught will be equal to sine inverse Pm by Pm1. Pm is equal to Pm P max 3 sine of delta 1, that is this delta 1. Since at this point Pm is equal to sine of P max 3 sine of delta 1. From here we can get the delta 1. Delta 1 is equal to sine inverse Pm by P max 3. So delta max is equal to pi minus delta 1, that is equal to pi minus sine inverse Pm by P max 3. Now using the equal area criteria to find out the uh, to find out the delta CR. So A1 is equal to, from this A1 is equal to integration of PM minus PE, where P is 0 from delta naught to delta CR. That's which we have done here. PM minus PE2, where PE2 is 0. So it is equal to PM uh, delta delta d delta from delta naught to delta CR. So when we integrate it, comes out to be PM delta CR minus delta naught. So what is area A2? Area A2 is the area between PE3 and PM. That is equal to integral from delta CR to delta max this PE3 minus PM. That is PE3 minus PM. When we integrate it and we get the value this. So equating area A1 and A2, this comes out to be this, and finally we can get the value of this delta CR, that is equal to PM by P max 3, PM by P max 3, pi minus delta 1 minus cos of delta 1. This is how we can calculate this critical clearing angle. Here also it's very difficult to find out. Here also we can find out the critical clearing time also, because here P is equal to 0 for this case. You can use this equation to find out the critical clearing angle. That is this equation, like we have done in earlier case. So this is the case when we have assumed the short circuit on one end of the line. Let us try to see the second case when the short circuit is away from the line, let us say in between the line. So we see that the short circuit is at this point. The equivalent circuit will be like this. Now, as I have told you earlier, that we need to find out, since these are two voltages V and delta, we need to find out between an impedance between these two, direct impedance between these two, or we can say yes, direct impedance between these two. Here you can see there is no direct impedance. We can have this XD dash and X1 which are connected in delta, and then this connected to ground. So there are different combinations. We need to find out a direct impedance between this point and this point, so that we can calculate the electrical power. So when the fault has not occurred, PE1 will be same as that of this one. PE1 remain the same. When fault occurs, we need to calculate it PE2 during the fault. For that, we need to do some conversions. Converting the delta constituting by x1, x1 by 2, and x1 by 2 into star, we get XC, XB, and XC on the three as the three impedance of the star. These are the uh, impedance of the three impedance of the delta. You can see they form the delta. This is x1, one side of this is delta, x2 by 2, one side of this is x2 by 2. They are like this. When we convert them into star, XA, XB, and XC, XA will be equal to x1 into x2 by 2 divided by summation of the 3. Xc will be equal to x1 into x2 by 2 divided by summation of the 3. Summation of the 3 will be nothing but x1 plus x2. Actually, it is x1 plus x2 by 2 plus x2 by 2. x2 by 2 plus x2 by 2 will be equal to x2. So similarly, xb will be equal to x2 by 2 into x2 by 2 divided by x1. So I have done it over here. Xe will be equal to xc because they are symmetrical. x1 into x2 by 2 divided by x1 plus x2 by 2 plus x2 by 2 to be equal to x1 plus x1 into x2 by 2 divided by x1 plus x2. xb will be equal to x2 into x2 by 2 into x2 by 2 divided by x1 plus x2. So the circuit will be like this. This is xd dash plus xc, then a parallel xb, then in series with v we have xc. That is this. Now further simplification, this xa dash I can write it as xa dash, where xa dash is equal to xd dash plus xa. I have simply added these two reactances. Now I have to convert this star into delta. Converting the star uh, made by xa dash, xb, and xa into delta, we get. Now this is xp. Xp is equal to, actually it should have been xa dash xb plus xb xc plus xc xa dash divided by xb. I have written over here inverse. So inverse of this xr is equal to, similarly this xb will be definitely parallel of opposite to this. Xp will be equal to opposite, sorry, uh, the summation multiplication summation of, you can see this, I'm not tell the statement, xc dash xp plus xp dash xc plus xc dash xc xe dash. It will remain same in the numerator in all the cases because it's inverse, will remain in numerator, but the denominator will be, for xp the opposite reactance is XB, it will be XB. For XR, that is XR, opposite is XC, it will be XC. For XQ, opposite is XC, that will be like this. But here, XP is the important one to be calculated, but because in equation it is only XP which has to be calculated. You can see now it is converted to this star has been converted to delta. We have one reactance over here, one reactance over here, and one reactance over here, like this. So we have one series and another two parallel. These two parallel have nothing to do with the equation, with the power transfer equation. Power transfer equation only does with this, because if you uh, calculate the power transfer equation by using this circuit or element omitting these two, the power transfer will still be same, because the voltage at point this and at point this will be same as the voltage at point this or this. So XP is important to be calculated. There is no need to calculate XR and XA as they are not required in any equation. The equivalent of the circuit now becomes like this. From this circuit we can calculate electrical power during the fault. That PE2 will be equal to EV by XP into sine of delta. There is no part to play by XR and XO. That's why they are not to be calculated. When this is done, P2 is equal to P max 2 sine of delta, PE1, where P max 2 is equal to EV by XP, and PE1 is equal to P max sine of delta, where P1 is equal to EV XT dash plus X1 parallel X2. By practice, you will calculate it. This XP will be very large as compared to XD dash plus X1 parallel X2. So PE1 is very large as compared to PE2. The post fault, when one of the line 2 is completely removed, it will be similar to case which we have already discussed. So PE3 will be equal to EV XD dash plus X1 sin delta, P max sin of delta, P max 3 sin of delta, while P max is equal to EV divided by XD dash plus X1. So PE3 is equal to P max 3 sin of delta. Plotting all this curve on the single graph we get, but we have to take in consideration PE1 is greater than PE3 is greater than PE2. PE2 is the smallest one, because XP will be greater than XD dash plus X1 plus, which is greater than XD dash plus the parallel combination of X1 and X2. Here you can see, first, during the normal operating, this system was operating at delta naught at this point, and this is the PE1. So everything was okay, but suddenly when fault occurs, the PE2 has changed from PE has changed from PE1 to PE2. So now here, since PE2 is very small, this area is to be accelerating area is to be calculated between PM and PE2. That is this one. Let us say, and now in this case I will directly calculate the limiting case, that is delta CR. In this case I will calculate delta CR. This is the angle at which we have assumed that at this point, when the fault is cleared, the decelerating area is just equal to the accelerating area. Now at this point, fault is cleared and line 1 restores the power to the system. That means at this point, PE changed from PE2 to PE3. Now decelerating area has to be calculated between PE3 and PM. So you need to be very clear about this. Now this is very simple. Delta naught is equal to sine inverse PM by P max 1. Delta 1, which is to be calculated because of this delta max, that will be equal to sine inverse PM by PM, P max 3. Delta max is equal to pi minus delta 1. So as we have done earlier, we can calculate the area A1. A1 is from delta naught to delta CR. This PM minus PE2. Here PE2, in earlier case PE2 was 0, but here it has got some value. So when we do this, we get A1 is equal to this value. Similarly, when we do the integration for area A2, it will be equal to integration of PE3 minus PM from delta CR to delta max, getting this, and we put the value of delta max is equal to pi minus delta 1. So we get this value and equate A1 is equal to A2. We get finally this value. So delta CR is equal to cos inverse of PM pi minus delta 1 minus delta naught minus P max 2 cos of delta naught minus P max 3 cos of delta 1 divided by P max 3 minus P max 2. So this is the simple simplification of it. You can get the value of delta CR here as well. The case 3 is the reclosure, use of reclosure. Now, from delta naught to, let us say, delta r, that is when reclosure has taken place. I will tell you what is a reclosure. You can say it is identical to that of this one. There is no difference from this to this. No difference of this. I have shown you one of this. What happens at delta r if the circuit breaker of line 2 are reclosed successfully, that is, the fault was not a permanent one but was a temporary one and therefore vanished on clearing the faulty line. The power transfer once again becomes equal to PE4, which is equal to PE1 is equal to P max 1 sine of delta. Usually what is done in case of faults, most of the faults you will see up to 70 to 80% are not permanent, they are temporary. Fault occurs and when you switch on the circuit breaker again, there is no fault. So it is therefore good to see first whether there a fault is permanent or not. Instead of going and seeing the whole the line, it will take a lot of time. So it is better to reclose it before, so that to ensure whether it is a permanent fault or a temporary fault. As I have told you that most of the faults in the system are temporary faults. So when reclosure is there, reclosure option is there for the circuit breaker. So the fault might have cleared already. You can see that when the reclosure, that means these two circuit breakers have been closed again. Which one? These two circuit breakers. The fault is cleared first. So the line is removed when the fault occurs and the line is removed. This is the same thing is done in the case C also until now. But um, before doing any inspection and then restoring this line after 1 day, half day, or any number of hours, these two circuit breakers are reclosed again to see whether this fault is permanent or not. If it is temporary fault, the fault clearing is successful, the power transfer will take place again, and the power transfer now will be governed by this equation, that is PE1. That is this equation why PE1 is this, because now both the lines are in series. So for this case, PE1 is equal to this. Now the P from this point, delta C, delta R, PE has changed from PE3 to PE1. Now you can see the decelerating area from this point to this point is between PE1 and PM, which is very large. Decelerating area is very large. Its stability has increased. So since reclosure restores the power transfer, the clearance chance, the chance of stable operation improves. So for critical operation, critical operation, this is delta CR, this is delta R, reclosure angle. You can see a lot of angle will be there, a lot of area will be there. You can calculate delta CR in terms of this delta R, delta max, and delta naught. So this is the equation where A1 should be equal to A2 plus A3. Area of dissolution has increased, stability has increased. By solving this, we can get this is here is one more thing which is important here. This delta max is equal to pi minus delta naught, not delta 1. In earlier cases, you can see that this delta max was equal to pi minus delta 1. You can see that this would have a lesser value, sorry, higher value, because delta 1 is very close to delta 1 is higher than delta naught, so this delta max would have been this lesser, but here delta max would be now greater than, though, so we can say that the stability has increased. So you need to identify these, what is delta max, what is delta R, and what is accelerating area, decelerating area. So I hope you have understood this. I will stop here.